you everybody who is watching this video. My name is Olenjolai Moko TAYAI Losingo. Simply call me Olenjolai. I'm from Tanzania, beautiful country in eastern of the African continent. I'm very happy to have you, whether you are a national or international viewer, who enjoying these contents. We have a good news in these online institutions, so you have to stay tuned in and stay focused and get prepared to receive wonderful materials for the rest, which will help you on solving real life problems. So I would like to welcome you into our online undergraduate Polytechnic Institute of Tanzania in square bracket Olenjolai M. Because that one of the departments is advanced in mathematics, one of the departments is higher engineering and scientific mathematics. So I would like to also take this moment to welcome you into one of our YouTube channels. We have 6 working, operating YouTube channels. This is one of them that called the Online Undergrad for Institute of Tanzania in square bracket Olenjolai M. So if you're a national, we'll be focused and use the syllabus of United Republic of Tanzania in some of the institutions, because you have TCU institutions and the institutions which are non-active, that is according to Tanzania. But remember that higher engineering and scientific mathematics, or even higher engineering mathematics and higher scientific mathematics, these are universal contents. So whether you're a national student or international students, you're gonna get so much in order to help you in acquiring your classroom instructions in engineering courses for undergraduate or in undergraduate science courses. So remember that you need this context, you have to stay focused. We are here in order to take you from one point to another point and to change your way of thinking and even the way that you define mathematics for the rest of your life. So that's the key point that we want you to be aware on that. But we'd like to remind you the vision that we have in online undergraduate Polytechnic Institute of Polytechnic Institute of Tanzania. This is the vision, and this is an assignment that God has given me as the founder of these online institutions. I have a responsibility to teach, to train, to incubate, to mentor, to lead some group of students who will be ready to take the classroom instructions in engineering, in fundamental and core modules of engineering, and also in fundamental and core modules of science and undergraduate level, and combine the knowledge extracted from the classroom instructions with the knowledge that you have to extract it from the Word of God, that is from the written in the Holy Bible, in order to solve real life problems. So that's an assignment. So we are going to teach you how you can extract knowledge from the classroom education. You combine that extracted knowledge, which is powerful, with the powerful knowledge from the Word of God, in order to use these 2 knowledge, which you can combine them and become into one which is superior, one superior knowledge, to solve a real life, either a real life problems in your community, a real life problem in your community, or real life problems in your community, in your country, in your continent, and elsewhere that you want to take this knowledge, because it's working in many cases. So that divisions. And the main goals of online undergraduate Polytechnic Institute of Tanzania is to see our continuing undergraduate students and even our graduate in undergraduate level students solving real life problems. Myself, I'm a product of both knowledge. I'm a product of the knowledge from the Word of God that reads the Holy Bible, from the book of Genesis chapter 1 verse 1 through the book of Revelation chapter 22 verse 21. And also I'm a product of the classroom instructions in our undergraduate education. So I used to combine these 2 knowledge to become one superior knowledge. And this is the one for the solution that I'm providing in the national and even international problem. What problems? You cannot learn mathematics on your own, so somebody has to teach you. So I'm here to solve a real life problems. I'm not answering the exams at this moment right now. I'm solving existing real life problems in the present and future generation. So that's the key point that you have to understand. We have so many departments in these online institutions. One of the departments is called Higher Engineering and Scientific Mathematics. We are going to teach you 12 modules or 12 courses in this department. And one of the course is called the calculus. This is, I say that I'm using the syllabus of Dar es Salaam Institute of Technology as representing all the institutions under NACTE, because the focus in under NACTE or National Council for Technical Education is competence-based. So we have the first chapter. We have 7 topics that we have to cover in this module of calculus. The first chapter is called Theory of Limit, or in some of the colleges or some of the institutions or some of the School of Engineering, they just call it limit. And hence we are in lecture 6. It means we have done 5 lectures already. So, and these 5 lectures, you can access them in YouTube channel, so you can go through them. And then there are formal definitions of limit at the subject of today. Again, we would like to invite you, and this is the content for the first year undergraduate students, not second year. So the year of study is first semester or first year. So if you are pre-undergraduate students, if you are pre-undergraduate student, then this is the first module that you will study when you be joining any institution. Again, I would like just to say that for instance, just the name of the module or the course will be different from yours. That's why that I insist always every students to have course outlines, whether you're international students or you are a national students. For instance, at the Arusha Technical, this is a DIT, right? This is DIT, according to the DIT, we call this one calculus. At the Arusha Technical, ATC, so students learn the modules, which is called the matrices and dotting and calculus. So the calculus that you cover at the Arusha Technical is the same with the calculus that you cover at the DLT. But here you have a new concept, which is called matrices, where the rest of the institutions are not learning it. But the good news also, there's another modules, which is the first one at University of Dar es Salaam, which is called the matrices and dotting basic calculus. I'm also teaching this module. So you see, so for the students of Arusha Technical College, they can benefit on this one. But again, they have another modules for the first year at University of Dodoma, which is called the linear algebra. So one of the topic is called the matrices, linear algebra. So you see that. So the point is, because I'm going to teach you 12 courses, so this is the quick review, 12 courses or 12 modules, right? So it means that you have to check the course outlines of your course or of your modules, and then you look the contents of it, and you come into the contents of each module that I'm going to teach you in this channel, modules or course. So I'm going to teach 4 modules of Dar es Salaam Institute of Technology. I'm going to teach 4 modules of 4 courses of University of Dar es Salaam. I'm going to teach 4 courses of University of Dodoma, because these are reference universities in the country. Okay, so then let me do the quick review of lecture. Quick review. So my dear students, recently I've taught you about I've taught you about lecture 5, and in lecture 5 I taught you about limit, how you can deal or how you can find limit of the particular function when the value of x approaches to negative infinity. So we say that this one also is we get our. Also, how can you find the limits when the value of x approaching to the positive infinity of the particular function f of x, this is equal to r. So if you find that limit as x approaches to negative infinity of f of x, this will be equal to the limit as x approaches to positive infinity of f of x, this is equal to r. Okay, so that's what we have discussed in the exam. So today I have a good news. I have what? I have a good news. You know what the good news? I want today to teach you formal definition of a limit. Say again, formal definition of what? A limit of the functions. So let us go inside. So we said that, remember that the concept of limit concepts of limit of the function, right? Limit of the function is a fundamental concept. So fundamental. So it's a fundamental concept in what? Calculus and what? And the analysis. So this is the fundamental. So we are building the foundations of calculus because the modules or the course we are calling calculus. So that's why that limit, the concept of limit, it is the first topic that we have to cover. And then we say that there are two definitions of limit of the function. Just to remind you, there are two definitions of limit of the function. Do you remember? The first one is informal definition, which I've been teaching you in lecture 1 to lecture 5. Informal. So informal definition. So informal definition. I taught this module more than 2,000 students in 5 years at the Institute of Technology. So I know what I'm teaching. So formal. But remember, Olenjolai does not know everything. I know small portions of calculus. Okay, formal definitions of the limit. And then the second one is formal definition, which I have to teach you today. Formal definition of a limit. So I want to relate the formal definitions of a limit with what you knew or you learned in informal definitions of a limit of the function. Limit of the function. Limit of a function. So then we said that recall the geometrical representation. Let us start from geometrical representation. Geometrical representations of informal definition. Informal definition of a limit. So you remember this X-ray plane. In case you forgot, I'm going to remind you. This is the y-axis. So this is an x-axis. And then suppose we have a certain curve which has been drawn with a certain function. And this certain function is called the f of x. Listen carefully. Then this is origin, where you have 0, 0. And then we say that suppose we want to start a limit of the function f of x at the point when x is equal to a. Right? Listen carefully. I want to add some piece of information. Then if you do remember that what I told you in lecture 1, I told you that x is less than a. You remember that? X on this side, all the values of x from here towards left hand side are less than what? The value of x which is equal to a. And I told you that in mathematics, these values of x's on the left hand side of a will notate them as x approaches to a negative one. Again, I told you that this is x greater than all the values on the right hand side of a are values greater than what? A. So I told you that in mathematics, we represent this phenomenon by having x approaches to a positive. Right? So that's the point that you have to remember. They've been doing testing. So listen carefully. We didn't concentrate on the y-axis, but on the y-axis, if we concentrate now, if the limit of left-hand side, the limits of the function f of x as x approaches to a bar is equal to the limits of the function of f of x, function f of x as x approaches to a positive bar, then the limit exists which is equal to r. Remember that. So we say that, if you do remember that, we say limit, this is what? This is figure 61. So we say that limit as x approaches to a bar of f of x, this also is equal to limit as x approaches to a positive bar of f of x, and this is equal to r. Right? So if it's equal to r, mean that values that will be as we approach a but not equal to a, the value of y will be r. Right? Will be r, because we obtain r as we approach a from left hand side, and also once we approach a from the right hand side, we get the same value. Then the limit of the function existing, and the value is it's what? It's a limit of that function. So you are familiar with this. I told you so many concepts, and this is the principle or the formula that will test whether the limits of the function existing or not. So I believe that you are competent enough on that. In case you forgot, you have to make sure that you review the contents for your benefit. Okay. So if that's the case now, we can consider now, we can go further, right? So we can consider now, we say that, let us consider figure 6.2 below. Okay, below. So let us consider this figure below. So here we have our y-axis. So this is origin, this is y-axis, this is x-axis, and then suppose that we still have the same function, which is graph is drawn here. So we say that we have some values. Suppose that this is x is equal to a, and then we have a dotted line like this one. So remember that we can still have the same knowledge. We say x less than a, and x we approach as a bar. Then I'm deducing the definition, the formal definition of the limit, and this is x approaches to a positive, right? Wow. So if this is the case, what do we say? We say that this is what? So this is our. Okay? This is our. So this is our. So then listen. Suppose that we want to test the value of y when the value of x is at this point. And then we say that we get also any value of y. Similarly, we can also take the value of y at this point, when now we have the corresponding value of L. So at this point, we can say that this is L minus small change in x. Listen carefully. At this point, because it is greater than A, this we call D. This is A plus small change in X. Similarly, at this side, we say that L minus what? Small change in Y. And also this side, we say that this is L plus small change in Y. Listen careful, right? So if that's the case, we say that, fine. So it means that if we reduce A by the small change in X, we also have the small change in Y, the corresponding small change in Y. If we also add the value of X, the small change in X, we have also an increment of value of Y, which is represented by the limit with the small change of Y. So, if this is the case, if you've understood about that, because that's what we have been doing when you drew the table, when you've been using the gaze concept. So we've been using that concept of approaching X is equal to A, or or approaching point A from left hand side and right hand side. So then we say that in mathematics, okay, we say that for the formal definition of limit, we say that small change in X, this is equal to delta. So this is called the delta. And then also for the small change in Y, right? The small change in Y, this we call it epsilon. In calculus we call it what? Epsilon. So this we call it epsilon. These are Greek letters. So now we take that. So you say that the geometrical formal definitions of a limit. Geometrical formal definition. Geometrical formal definition of a limit. Geometrical formal definition of a limit. So you can define, you can present these formal definitions of a limit geometrically. Let me present it in, we say that formal definition of a limit of a function can be represented geometrically, right? Can be represented geometrically as shown in, this is figure 6, figure 6.2. In figure 6.2 below. Okay? Now figure 6.3, because this is 3. So let me draw, show you now, before we define, before we write a sentence, before we use it to prove or to test whether the given limit or predicted limit of the functions is true. Because that the functions of floating, that's applications of formal definition of the limit. Okay, so then we have our function, which is f of x. This is y-axis, this is x-axis, y-axis and the x-axis. This is origin, 0, origin. And hence we want to present formal definition of a limit of a function. Are you ready for that? Okay. So suppose that this is the point. Suppose that this is the point. This is the point. So say this is A. Okay? Okay? So let me extend like this. And then let me extend like this. And then let me extend like this. And let me extend like this. Okay. Excellent. So then we say that the small change in x, we call it, this is A delta. Small change in x corresponding to sorting is delta. We eliminate this because this is known. So this is the origin. So we say that here we have A, and here we have A minus delta, and here at this point we have A plus delta. On this side, in the y-axis, we have limit because which corresponding to A. As x approaches to A, we have a limit. Here we have limit minus what? Epsilon, which is small change in y. And here we have limit plus what? Epsilon. My dear student, one of the challenging concepts on my own when I've been learning the theory of the limit is formal definition. Really, I spent a month learning about formal definition on my own, and I understood nothing. I went to the normal class, physical class, analog class. I've been taught by a PhD lecturer, right? PhD lecturer in mathematics, right? And then I've been taught formal definitions. I understood nothing. I don't mean that it is a difficult concept, but I want you to be serious once we are learning about formal definitions, because it's a kind of the pure mathematics, not applied mathematics as the one that we learn as the engineers. Okay, so that is the representation. So we have our FFX there, and then so we have L plus these epsilons, L minus epsilon, and then so we have L, so we have A minus delta, and then this is what so this is figure 6 and 3. So that is geometric representation of what formal definitions of a limit. So let us go literal representation now. How can we present this definition as a sentence and have a formula and you see its application? Then I'll take you on problem solving of this subtopic of limit. Okay? So now, say that formal definition of limit. Formal definition of limit of a real value function, of real function, because you have also formal definition for complex function. Okay, so we say, so this is the way that we can state it. So we said that we can let f of x to be defined for all values which is for all x is not equal to a over an open interval containing a let L be a real number. Again, say that let us let it out to be a real number, then limit as x approaches to a of f of x. This is equal to real number L, which is limit for every value of epsilon should be greater than 0, means that epsilon should not be negative, as we showed there. There existing the corresponding value of x, which is delta, there existing a, which is greater than delta, which is greater than 0, okay, such that if 0 is less than absolute of x minus a, then absolute of 40, then absolute, then delta of 40 less than delta, right? Then absolute of f of x minus L, this is less than epsilon. This is different formal definition of a limit. Seem like long, but we can summarize because the first sentence is known for you. So what you've added is just the next values. So let f of x to be defined for all x is not equal to a, it means the limit of an open interval containing a. Let L to be a real number, then the limits of the f of x as x approaches to a, but x is not equal to a, is equal to r. For every epsilon greater than 0, there exists a delta greater than 0, such that if 0 less than absolute of x minus a, absolute less than delta, then absolute of f of x minus L is less than what? Epsilon. We can also, or we can define this one and say that given the limit as x approaches to a of f of x is equal to r, right? And then we say that if for epsilon greater than 0, for every epsilon for every epsilon greater than 0, there exists a delta greater than 0, right? Greater than 0, so that such that if 0 less than absolute of x minus a less than delta, right? Then absolute of what? Of f of x minus L less than what? Epsilon. So these are another definitions of this. There are summarized definitions of what of formal definition. Right? For every epsilon greater than 0, there exists a delta greater than 0, such that if 0 less than absolute of x minus a less than delta, then then we say that absolute of f of x minus l is less than what epsilon. So after giving you the formal definitions of the limit, let me explain in brief applications of what? Applications of formal definition. But before application of formal definitions, I would like to present to you the unique characteristics of this formal definition. Formal definition, first of all, is a precise definition of limit. Is a precise definition of limits. Precise definitions of limit at finite points at finite points, the finite values or limits that are infinity and limits at infinity. Finite values points. So formal definition is a precise definition of limit at finite points. So this is formal, and this is the precise. Means we say that in formal definitions, not the precise definitions of the limit. So let us go to another part before we solve problem. Applications of formal definition. Applications of formal definition of a limit. What are the applications of informal definition? If you don't remember, I told you. What application of informal definition? Tell me in the comment section. So we have one famous application of formal definition, which is this one. Say that the formal definition of limiting of the function is used to test, to verify, or testing the suspected or guessed suspected what? Testing the suspected limiting of the function of the given function. Suspected limiting of the function. So it's used to verify or test the suspected limit of 40 of the function. So note this. Formal definition. Formal definition is not used to find limit of the function. What is used? Which definitions is used to find limit of the function? It's the one that I taught you in lecture 1, 2, 3, 4, and 5, which is informal definition. And if you have any question, don't hesitate to ask yourself. So he said that we are learning the formal definition because we'll be given some of the problems which the limit has been predicted. So we are the higher engineering mathematicians or higher scientific mathematicians, or both higher engineering and scientific mathematicians. We will be asked to prove or to show that the limit of that function is correct. Right? So if that's the case, okay, I think that's better if you go into the numerical examples. Numerical examples. So get prepared to go into the so in the previous session, which was lecture 5, I left a homework, which was example 11, if you do remember. And this homework was saying that the first question, what is formal definition? I want just to do correction. Formal definition of the function, right? So I don't know if you've done your homework, but now I've answered, you know it. And then the second question then that represents formal definition geometrically. And I did geometrically. So I did this in figure 6.3. So I didn't write the number of example. Issues, I didn't write number of example. I wrote just example 5. I didn't write the number of example, but it's example 11. So now, ladies and gentlemen, let me take you into example 12, where I have now to put on the blackboard a question of that we have to use formal definition to show that limit as x approaches to 1 of what? Of our function is 5x minus 3 is equal to 2. So use any constant that you know to show that limits of 5x minus 3 as x approaches to 1 is 2. Right? So this is the solution. And if this is the solutions, we say that this is the first step. First step means that we call what? We call formula of 40 formal definition. This is what you've done there. That's the formula for the formal definition. At the first step. Right? So we go for the second step now. In the second step, for we are given what? So he said that yes, compare the general formula with the given function. Or he said that substitute the values. Okay, substitute values. So what does it mean? So when you take a focus on this part, we say that we have what? The big given what limit as x approaches to 2, as x approaches to 1 and 2. So this is limit as x approaches to 1. Then our function is what? 5x minus 3. This is equal to what? This is equal to 2. So the general formula is what? 0 less than absolute of x minus a, less than delta, and this will be implies what? Absolute of f of x minus L less than epsilon. So you have determined to substitute the values. So it means for this case, a is equal to 1, and then say what? F of x is equal to what? 5x minus 3, right? And then say L is equal to 2. You don't know the value of epsilon, you know the value of delta. So that's what he says, substitute the values. So substitute the values right now. Remember that this arrow, this implies we have on the left hand side we have 0 less than absolute of x minus a, which is 1. And this one also will be equal to less than 40 delta. And this will implies what? Absolute of f of x, which is what? F of x is 5x. It's 5x. Listen carefully. And as what? Minus 3. What is that? 2. And less than what? Epsilon. So we can simplify it. 0 less than absolute of x minus 1 less than delta. And this one is what? It is 5x minus 5 less than what? Epsilon. So this is, it is what in question 1. My dear student, I would like to ask you to stop writing, listen, and look careful. As I will be insisting you, be careful on learning formal definition of the limit because they're kind of confusing. So stop writing, look the way that I'm going to solve because we're going to use some assumptions. Okay, so that the first step, all about first step, so we go for the second step. This symbol is what implies. So we have left hand side and right hand side here. So the second step, we say that let us consider the right hand side of 40 of equation 1. So the right hand side of equation 1, this is absolute of 5x plus 5 less than what? Epsilon. Right? Then we find 5 is common. So you can take absolute of 5 out and remains x minus 1 less than epsilon. Absolute of 5 is equal to 5. So 5 absolute of x minus 1 less than epsilon. Divide by 5, divide by 5. So then we find that absolute of x minus 1, this is less than epsilon over 5. So this is equation what? 2. So in this fact now, what do we say? We know, but we do know. But we know that absolute of x minus 1 above, this is less than what? Delta. And this implies that, you can say that this implies what? That absolute of x minus 1, this is equal to delta. So now, if that's the case, we go for the same step. So the same step, we can choose. We can choose now, because we are looking for the value of epsilon. We can choose that our delta is equal to epsilon over 5. This one. Epsilon is of 40 over 5. So if I ask you to stop writing, just to look how am I solving this problem. And we'll have so many questions for you to practice on your own. So, so you know that because on left hand side, so we say that in left hand side, we know that this one is less than delta and delta is equal to that one. So you can take a delta is equal to epsilon over 40 over 5. So we can choose, right? This is choose. We can choose, not we can choose. We can choose. delta is equal to epsilon over 5, right? So if that's the case now, the problem is very interesting, right? So again, we say that we go for the first system. The first system, once again, that we say that, okay, consider right hand side of 40 equation 1. So if you consider right hand side, we have absolute of 5x minus 5 less than epsilon. So listen carefully. So then, if this is the case, you say that this is equal to what? 5x. Okay, 5 is common, so you take 5 out. And then you have absolute of x minus 1. And this is less than epsilon. Right? So absolute of 5 is 5. And less than x minus 1. And this is less than epsilon. Right? So, but we have said that. Yeah, we have said that absolute of x minus 1, this is less than delta, and this implies that absolute of x minus 1 is equal to delta. But also say there delta, we choose delta is equal to epsilon of 1 over 5. So if that's the case, you have 5, and then in absolute sign there, we are going to introduce the value of delta, and then this is less than epsilon, or equal to epsilon. And then you find that 5. What the value of epsilon that we chose of delta? It is epsilon over 5. So then this is equal to what? Because it's equal to epsilon. So we find that epsilon is equal to epsilon. So we say that hence, show, if you achieve this one, show, hence show that the limit of 3x minus, or 5x minus 3 as x approaches to 1 is equal to 2. So this is the way that we have to show. We have to prove. I know that you understand less. It's just like you're still amazing. How did we solve this problem? So because I know your situation right now, I may give you the second example. Keep on listening, or you can pause the video, you can copy the previous solution, but again concentrate on the second example, which I'm going to solve in order for you to have this concept in your mind for the rest of your life. So this will make example 13. Okay, example 13. The question said that use the definition. Some of the books use the epsilon delta definition of 40 of the limit. Do you enjoy the beauty of sort of limit? To prove the following limit. Prove the following limits. Prove the following limits. Prove the following limit. This limit is what? Limit as x approaches to 2, then you have 5x minus 4 is equal to 6. So use the definitions of the limit to prove the limit of the function 5x minus 4 as x approaches to 2 is equal to 6. So solution. Then solution. The first step, as I told you in the previous example, we call what? We call the formula of 40 or form of definition. Formal definition of what? Formal definition of limit. How does it state? We say that given what? Given limit as x approaches to a, f of x is equal to L. And we say that for every value of epsilon greater than 0, say that there exists what delta greater than 0, right? Delta greater than 0. There exists delta greater than 0. So then we say that 0 less than absolute of x minus a absolute minus delta. This implies what absolute of ffx minus L. Yes, this is less than what absolute. Okay, so if this is the case, now we go for the second step. So the second step, we say that compare, can call it to compare the given function, FCT means function, and vertical, and this standard formula of 40 of formal definition. Some of the books they call it epsilon delta definition. Okay. So if we do compare, we'll be given what? We'll be given limit as x approaches to what? Approaches to 2. Then this is 5x minus 4. This is equal to what? 6. So if we do compare that with limit as x approaches to a, f of x is equal to r. So a is equal to 2, f of x is equal to 5x minus 4, and then limit L is equal to 6. Right? And afterward, we think that we can go to the steady state. Steady state is going to substitute values of 40, values of a, L, and f of x in formal definition. So how? 0 less than x minus a, which is 2, less than delta, and this implies what? And this implies that absolute of f of x, which is 5x minus 4, minus L, which is 6. This should be less than what? Absolute. Right? So if you simplify, this is implied. So this is a set of implied. But the Washington, right? Okay. So we enjoy the beauty of calculus, of higher engineering and scientific mathematics. So if you simplify, this is 0 less than absolute of x minus 2 less than delta, and this implies what? Absolute of what? 5x minus 10 less than epsilon. So this will be our equation 1. So we go for the first state. So in these solutions, because now we have begun to understand, then that's why that we have more, that we'll have so many steps for you to understand and go through it. First step. So the first step, we say that consider writing hand set of 40, right hand set of equation 1. So if you consider right hand side of equation 1, you have absolute of 5x minus 10 less than epsilon. So 5 is common, so take absolute of 5. So if you take absolute of 5, this is x minus 5. No, x minus 2, excuse me. It's x minus 2, right? And this is what is less than epsilon. Listen carefully. Stop writing, listen carefully. So what the absolute of 5? It is 5. And then you have x minus 2. This is less than what? Epsilon. So divided by 5 on this, on the left hand side. and divided by 5. So you have absolute of x minus 2. This is less than epsilon over 5. Okay, epsilon over 5. So if that's the case, we go for the fifth system. Okay? We go for the fifth system. So you go for the outing for the fifth system. So the fifth system now, after you've got that the value of, remember that the fifth step, we said that absolute of x minus 2 from equation 1, this is less than epsilon, this is less than what epsilon, and this implies that absolute of x minus 2, this is equal to delta, delta. So now, because we know the value of delta, we can choose the value of delta to be epsilon over 5. And then so we find the value of epsilon at the case that we're doing. So afterward, we say that you go for the sixth step. The sixth step said that now consider the right hand side of what? Of equation 1. Right hand side, we still consider right hand side, because we are looking for the value of epsilon. Why? It's just like in informal definition, we'll be looking the limit. So even here, we should know the value of delta in order to find the value of what? Of epsilon. So the part of right hand side is 5x minus 10. This is less than epsilon. So 5 is common, so you take it out. So you have x minus 2. It's less than what? Epsilon. Absolute of 5 is 5. X minus 2 less than epsilon. Over 5 over 5. So then absolute of x minus 2, should not divide. If you, after we reach this step, we say that know that absolute of x minus 2, this is less than what? This is less than delta, right? Which is equal to delta if you remember. This implies what? Absolute of x minus 2 is equal to delta. So if that's the case, you say that this is 5 times delta, right? 5 times delta. Or say that 5 times delta. Is this equal to epsilon? What did we choose? The value of delta. It is what? Epsilon of what? Over 5. And the answer will be what? Epsilon. So if you achieve this one, then we say that hence shown at the limit as x approaches to 2, and then the functions was what? 5x minus 4 is equal to 6. That's the response of that question. Interesting. And now, I believe that you are beginning to understand. Don't worry. Lecture 7 will be also formal definition. Possibly lecture 8 will be also formal definition. So that you have to understand and keep this piece of information for the rest of your life. So now it's a time for exam point. You solved example 12, example 13, example 14. And this example 14 is the end of this session. It's homework. And this is homework what? Homework 6. So homework 6. And this is example what? 14. I need 2. Prove that. We don't tell you that which definition may you use, but you have to understand, prove that this is the questions of limit of the function. As limit, the limits of 3x plus 5 as x approaches to 10. Prove that the limit of 3x plus 5 as x approaches to 10 is equal to 75. The good thing of these questions, if you ignore the condition that x should not be equal to 10, and you substitute it here, so it means 10 times 3, 30 plus 5, 35. So you see from prediction, but you have to show that it is true, that these expressions, the limits of this function, 3x plus 5, which is linear function, is 35. So then that's all about the beauty of formal definitions. I built the foundations. I believe that. I thank God who have created me in his image and likeness. And I thank God who have given me the gift of teaching, that to teach you and even to teach your children, so the children's present and future generations. I thank God who have enlarged my tent of teaching. So right now I can teach national, international student, present and future generation. He the one gave me this idea and he owns it. I thank God who have given you a chance to be with me and learning this good news with me. And may God bless you abundantly. I invite you in lecture 7, when I'll be solving so many problems about formal definition. And I invite you also in lecture 8, when now we teach you how you can find the value of delta for a given item. Value of delta, let me check the value for, finding delta algebraically for given value of epsilon. So that's what we teach you in lecture 8. So don't miss. Make sure to share these contents we go through. In case you have any questions, ask in the comment section. Remember to subscribe to our channel. Remember to share these contents with your colleagues, with any of your colleagues that is doing undergraduate studies in first year in any institutions, in any college, and also in any university. Make sure also read the descriptions below for you to get so many informations, including the bank transaction in case you want to offer your free will in Thanksgiving in order to support these programs, or in order to support online diploma polytechnic institute of Tanzania. You don't need just the help or just the money, because the money we have been asked to receive offerings. Okay. So then remember that you can send your free will in Thanksgiving offering to God through Olenjolai or through online diploma polytechnic institute of Tanzania. So how? You can use the telephone number 0759 745331 and you'll be participating on what that you'll be receiving, especially that on the different contexts, so that you will be having so much to cover. So may God bless you. I thank you very much for being with me, and may God keep you until we meet once again in the lecture 7 of 14, which will be all about formal definition. Thank you very much. May God bless you. I'm praying for you. Pray for me. May God bless and keep you for the rest of your life.